Alpha soils. Alpha soils are moderately leached soils that have relatively high native fertility, forming primarily under forest or mixed vegetative cover, and are among the most important soils for agricultural production globally. These soils are found in temperate, humid, and subhumid regions of the world, making up about 10% of the ice-free land surface on Earth. Because they have an abundance of essential nutrients like calcium, magnesium, and potassium, alpha soils are highly productive for both agriculture and forestry, functioning much like a well-balanced natural fertilizer system for crops. The subsurface horizon of these soils is enriched with silicate clay that has moved downward from the surface layer, creating a distinct profile that holds moisture exceptionally well during dry spells. Major regions operating with alpha soil-rich lands include the Ohio River Basin in the United States, parts of Western Europe, and regions of Southern Australia. Understanding alpha soils is a great starting point for our journey into every soil type explained, as they demonstrate how natural clay movement and forest ecosystems work together to create incredibly stable and fertile environments that have historically supported dense human populations and extensive farming. Andisols. Andisols are a unique type of soil that forms in volcanic ash and other volcanic ejecta, making them intrinsically tied to the geologically active regions of our planet, often referred to as the Ring of Fire. This soil order is characterized by its exceptionally high water-holding capacity and its ability to naturally fix large amounts of phosphorus, which is a crucial nutrient for plant growth. Even though they only cover about 1% of the global ice-free land area, andisols are incredibly productive and fertile, supporting intensive agriculture in regions that might otherwise be too mountainous or geologically volatile for traditional farming. You can think of andisols as the Earth's natural sponge, as their unique volcanic glass composition allows them to absorb water and nutrients rapidly and hold onto them tightly. Major countries and regions featuring prominent andisol deposits include Japan, Chile, Indonesia, the Pacific Northwest of the United States, and the fertile slopes of Hawaii. The physical properties of these volcanic soils make them highly resistant to erosion, but incredibly light and fluffy, meaning that while they are easy to till and manage, they require specific agricultural techniques to release the trapped phosphorus for crop use.
Aridosols. Aridosols are the soils of the world's deserts and dry lands, characterized primarily by their extreme lack of moisture, which severely restricts the growth of plants and the natural weathering processes that typically break down minerals. These soils cover about 12% of the Earth's ice-free land area, making them one of the most widespread soil orders on the planet, dominating regions where evaporation exceeds precipitation. Because there is not enough water to wash minerals out of the soil profile, aridosols often accumulate large amounts of calcium carbonate, gypsum, salt, and sometimes even silica, forming hard subsurface layers known as hardpans. While their dry nature might make them seem completely barren, aridosols can actually be highly productive for agriculture if they are properly irrigated and managed to prevent salt accumulation. Countries heavily defined by aridosol environments include Saudi Arabia, Egypt, large parts of Australia, and the southwestern United States. In these regions, farmers and land managers must operate with strict water conservation strategies, acting much like desert survivalists who carefully calculate every drop of water, because over-irrigation can cause the natural salts in aridosols to rise to the surface, rendering the land toxic to most conventional crops. Entisols. Entisols are soils of recent origin that show very little to no development of distinct soil horizons, usually because they have formed in areas where the rate of erosion or deposition is faster than the rate of soil formation. Accounting for about 16% of the global ice-free land surface, entisols are the most extensive soil order on Earth, found in a massive variety of climates and environments, from steep rocky mountain slopes to the active floodplains of massive rivers. Because they are so young in geological terms, their properties are almost entirely dictated by their parent material, meaning an entisol formed from river sand will behave completely differently than one formed from a recent landslide of dense clay. Some of the most agriculturally productive lands in the world are entisols found in river valleys and floodplains, where rivers constantly deposit fresh, nutrient-rich silt, similar to how a delivery service constantly drops off fresh supplies to a restaurant. Major areas with prominent entisols include the vast Sahara Desert, where moving sand dunes prevent long-term soil development, as well as the heavily farmed floodplains of the Nile River in Egypt and the Ganges River in India. The sheer diversity of entisols means they serve endless ecological roles, offering everything from unstable, shifting habitats for desert wildlife to rich foundational beds for continuous human agricultural civilizations.
Gelisols. Gelisols are soils of very cold climates that contain permafrost within 2 meters of the surface, making them a crucial component of the Earth's polar and high-elevation ecosystems.
These soils cover approximately 9% of the world's ice-free land area and are defined by a process called cryoturbation, which is the physical disturbance of soil materials caused by the freezing and thawing of ice. This constant churning creates chaotic, mixed soil horizons and unique surface features like patterned ground, ice wedges, and frost boils. Because the extreme cold drastically slows down the decomposition of organic matter, gelisols store massive amounts of carbon, acting as an immense global freezer that traps greenhouse gases safely underground. Major regions completely dominated by gelisols include the sprawling tundras of Siberia in Russia, northern Canada, Alaska, and the ice-free coastal regions of Antarctica. Climate scientists study gelisols with intense scrutiny today because as global temperatures rise, the permafrost within these soils begins to melt, threatening to release centuries of stored carbon and methane into the atmosphere, which would further accelerate global warming in a dangerous feedback loop. Histosols. Histosols are essentially organic soils, forming in environments where organic matter accumulates at a faster rate than it decomposes, which typically happens in waterlogged areas like bogs, moors, peats, and mucks. Making up only about 1% of the global ice-free land area, these soils are composed of at least 20 to 30% organic material by weight, contrasting sharply with most other soil orders that are primarily mineral-based. The continuous presence of water restricts oxygen availability, which prevents microbes from efficiently breaking down dead plant materials, allowing deep layers of dark, rich organic matter to build up over thousands of years. Histosols are highly prized for specialty crop production, particularly for growing things like cranberries, onions, and mint, but they are also incredibly fragile and will rapidly subside or even catch fire if they are artificially drained. Extensive regions of histosols can be found in the peatlands of Finland, Scotland, Indonesia, and the Florida Everglades in the United States. Just like gelisols, histosols are massive carbon sinks, and protecting them from drainage and overharvesting is considered an essential environmental strategy to prevent the release of their densely packed historical carbon back into our atmosphere.
Mollysols. Mollysols are the highly prized soils of the world's grassland ecosystems, renowned for their incredibly thick, dark surface horizons that are exceptionally rich in organic matter and crucial nutrients. These soils account for roughly 7% of the Earth's ice-free land surface, but are arguably the most important soil order for global food security, as they produce the vast majority of the world's commercial grain harvests, including wheat, corn, and soybeans. The deep, fertile topsoil of a mollysol is created by the continuous life cycle of prairie grasses, whose deep root systems grow, die, and decompose underground year after year, building up an immense reserve of calcium, magnesium, and organic carbon. You can think of mollysols as the agricultural gold mines of the planet, requiring much less chemical fertilization than other soils because of their naturally superior structure and high baseline fertility. The major agricultural powerhouses of the world operate primarily on mollysols, including the Great Plains of the United States, the Pampas of Argentina, the vast steppes of Ukraine and Russia, and parts of northern China. Protecting these phenomenal soils from wind and water erosion is a top priority for modern agronomists, as the incredible natural wealth contained within a mollysol topsoil can take hundreds to thousands of years to naturally regenerate if it is blown or washed away.
Altisols. Altisols are strongly leached, acid soils found primarily in humid temperate and tropical regions, representing a very advanced stage of soil weathering that is just one step behind the extreme state of tropical oxisols. Covering approximately 8% of the Earth's ice-free land surface, altisols are characterized by a subsurface layer enriched with clay that has migrated downward over time, coupled with relatively low native supplies of basic plant nutrients like calcium and potassium. The high weathering means that their iconic red and yellow colors are prominent due to iron oxides, but unlike oxisols, altisols still retain some weatherable minerals and a distinct clay accumulation layer that can cause waterlogging if not properly managed. While their natural acidity and low fertility pose challenges, altisols respond incredibly well to good management practices, and with the proper addition of fertilizers and lime, they can become highly productive agricultural lands. The southeastern United States, large areas of Southeast Asia, and parts of South America are regions heavily defined by the presence of altisols, supporting massive cotton, tobacco, and timber industries. Understanding altisols reveals the delicate balance of long-term soil aging, showing how ancient soils can lose their natural chemical wealth while still providing a robust physical foundation
for both intensive human agriculture and thriving, dense forest ecosystems. Thank you for watching. If you found this video helpful, please take a moment to subscribe to my channel right now for more highly detailed educational videos. Thanks for watching.